Hello, everybody, and welcome to the Quantum Technology Training for Policymakers. Today, we are going to talk about a topic that has not yet been in our agenda for the last three cycles, and it's going to be dedicated to how quantum technology impacts the law enforcement. And as always, I think a lot the Quantum Flagship Coordination Action, QCADS, that has been managing and organizing these trainings, and in particular the CNR, National Research Council of Italy, which was taking the leading role in preparation of the sessions. Now, I would like to go directly to introducing our speakers. And just a quick note before that we will be receiving the questions from you through the Q&A box. Please be attentive and put the questions there, not in the chat, otherwise you might be lost. And now I come to introduction of our speakers. So our first speaker today, whom I invite to join, is Dr. Iwen Coisel. I invite him to join the stage and share his slides. And in the meantime, I'd like to introduce him. So Iwen has been a digital forensic examiner at the European Cybercrime Center at Europol since May 21, where he focused on the decryption of digital evidence in operational investigations. He received his PhD in cryptography from Orange Labs in France in 2009, and previously he held research positions at the Université Catholique de Leuven in Belgium and the Joint Research Council at the European Commission in Ispra, Italy. His work spans through cryptography, cybersecurity, digital forensic, password cracking techniques, and password strength metrics. And more recently, his work has turned towards the implications of quantum technologies for law enforcement, exploring both the cryptographic threats posed by quantum computing and the opportunities it may create for the future digital investigations. And 2 years ago, Iwen coordinated a joint report between the Europol and Joint Research Center of the European Commission about the implications of quantum technologies of different types, sensing, communication, as well as computing, on the law enforcement. And we are looking forward for the presentation of Iwen about these implications today. So Iwen, the stage is yours.
Good morning, everyone. Thank you, Oxana, for the kind introduction. And I will directly jump into the topic. And I first would like to go a little bit back in the past just to remind that, in fact, quantum mechanics is not something new. We are living in the quantum world. And quantum mechanics is not a human invention, but it's a discovery. And what we are doing, in fact, is using the quantum mechanics to deploy a new application. And in fact, it's not something that is completely new. We are already using for a long time the quantum atomic clock, for example. We are using laser or MRI. And also something that was still a decade ago, something quite pure experimental. Now we have, for example, the Euro QCI that is using the quantum channel to secure our communication. And this is already deployed in practice. And so just to remind that quantum mechanics is not new. But I also want to say that whenever we are using new technologies, there is still an uncomfortable truth that quantum technology is not an exception. And this will be a shield for some people, but can be also a weapon for others. And criminals will equally make use of those techniques to their own advantages. If I take the particular example, for example, of machine learning will probably benefit from a huge boost from quantum techniques. And this will be potentially used by law enforcement to increase the usage of machine learning, for example, to discover non-obvious patterns in large investigative datasets. This can also improve biometric matching, for example, but this at the same time can also be beneficial for criminals that can use quantum-boosted machine learning to identify weak links in fraud detection system, iterate faster their own attack models, or also optimize their malware evasion with limited data. And in a more broader sense, I think law enforcement will face quite a lot of new operational challenges that will be enabled by quantum technology. For example, this quite famous now, the fact that quantum computers will break current classic cryptography. This also can be the secure communication channel. We will have probably more difficulty to get access to the data used by criminals. They will optimize their criminal activity. They can have the quantum enhanced AI, as I already mentioned, but they can also use, for example, quantum sensors to detect better physical vulnerabilities in system. At the same time, while this is a challenge, this also be potentially an opportunity for law enforcement. And for example, we can also use quantum technology to break cryptography and get easier access to data of criminals. And we can also use the secure communication channel to better exchange investigation data among the countries and partners. We can also optimize the law enforcement activity thanks to the quantum optimizer, and we can benefit from quantum and AI, and again, also quantum sensors. So it's really important to understand that there is clearly a mix of challenge and opportunities. And if I may, we can even use the term superposition, which is quite quantum, nice word. So we have to pay attention to this. There is one thing that you can hear everywhere is that for sure quantum computers will change the world. A lot of people are speaking about the crypto apocalypse. You can read lots of paper that people have already been able to break military-grade encryption. So you really need to pay attention to those documents, because when you start reading at it, for example, there was a Chinese paper claiming that they have broken the military-grade encryption, and at the end of the day, they were using a very nice technique to break RSA with 50 bits. And I'm personally convinced that the military are not using 50 bits RSA key, but more bigger ones. So we are still safe. What is interesting to look at is what would be the timeline we are speaking about when those quantum computers will be able to break cryptography. And for this, there is a very nice report published every year by the Global Risk Institute, which is asking experts, and in this case of the report of 2024, that was 32 global experts from academia and industry, including also Shor, the creator of the Shor's algorithm. And they are asking when they believe that this quantum computer would be able to break an RSA key in 24 hours. I think that this timeline shows that there is no certainty. And when you read different reports, you will see that some report mentioned that it's going to be in 5 years. Some others says we don't know. Some others says it's going to be 10, 20 years. What is certain is that it looks like now we are sure that this will happen in a somehow close by future. So what is sure is we need a transition. So I want to recall this Mosca inequality that has been designed in 2015, that the transition to post-quantum algorithm is not instantaneous. There is no magic button that we will press one day and we will change from classic cryptography to post-quantum cryptography. So this will take time. And until the very last day of this transition, we will still use some classical cryptography. And maybe some of those messages will be needed to be conserved secure for a certain period of time. And so if we put in parallel the time before the quantum computer will break the cryptography, it might be that there will be a time that we will be able to decrypt some messages that still needed to be secure. And that's where we have the danger zone. So we can face something that is called a store now, decrypt later. You store the communication today, hoping to be able to decrypt them later in the future. I personally believe that this fact should not impact law enforcement too much. The first reason is that I hope that the law enforcement, as any other agency and member state, will start the transition soon enough to be on the safe side. And I also believe that when the quantum computer will be available, the first quantum computer, the first prototype, will not be made available to criminals. So I believe that those communications from law enforcement will be safe, and we will probably see some attack at the member state level, and this does not fall into the law enforcement agenda. And on the other side, can law enforcement use the store now decrypt later in criminal investigation? I also don't think this is relevant. The first thing, I don't know, sorry for that, but if there is any legal basis that allow us to store the data for a long period of time. And also I'm quite convinced that if I go back to a prosecutor asking him, is that okay for you if I store the data now and I will solve your case in 30 years? I'm quite sure the prosecutor will tell me, no, I want you to work on this today. So that's why I believe the store now decrypt later should not really impact much the law enforcement. But there is another point that we are quite aware of the risk that quantum computer will represent for the security today. But there is something that is probably not said enough, even if everyone knows, is the transition now matters more than the break itself. Because we know that security will be broken and we are working towards this. But the transition is also something that is particularly at risk, because if you don't take care enough, then you can do mistakes. And while we know that we should act quickly, we should also not confuse speed with precipitation. If, for example, some member states or any agency or private industries have decided to already move to this algorithm that is called PQC, that was one of the candidates of the NIST standardization, this one has been revealed at a quite late stage to be broken and using classical means, not even using quantum means. So that's why the transition, there is a bit of a danger zone in the transition. What is for sure is that this transition to post-quantum cryptography is unavoidable. It's going to be long, it's going to be complex, and it might involve hybrid cryptographic approach. Those approaches means that we will use a combination of classic cryptography with post-quantum cryptography. So that if it reveals that post-quantum is not as safe as we were expecting, we can still rely on the classic cryptography security for a while. But this will increase even more the complexity. And with complexity, you also increase the attack surface because you can have lots of implementation, integration errors. So that's a real challenge, and we should be really cautious about this. And another point I want to underline also that there is an additional challenge in international collaboration. In the EU roadmap, they really encourage the member state to start drafting their own strategy roadmap, and they encourage also them to synchronize and collaborate. But you can already see that in some of the standards, you will have some country that will select a subset of the NIST standards. Some other people will go for a completely different one. And if you don't have any intersection in those decisions, maybe the collaboration will become quite complex. I can only encourage you to read this report that has been written by the JRC in December 2025, which underlined the post-quantum cryptography, the journey so far, and the challenges ahead. It's a very nice summary of all the existing standards, but also what is already ongoing at different member states and international level. So this being said, as I'm always saying, there is this dual use. And so with this complexity, there will probably be also new ways to access data. Those standards that have been decided by the NIST and also all the other standards that are coexisting today, they are not as mature than the historical ones. If you go back in the past, RSA was designed in 78, and it has been evolving all along the years because new vulnerabilities have been discovered and they have been evolving in the standard. And just an example, again, the PQC was broken with classical means while it was designed to be secure. Another example is that if you look at the NIST selection of candidates, most of the standards rely on lattice-based cryptography. And it's a new mathematical problem on which we rely for security, but there is no attack known so far. Like RSA was relying on the factorization problem, there was no attack known until Shor came with his algorithm and expecting quantum computer. So that's a little bit of a problem because if one day someone comes with an attack on lattice-based cryptography, then all the new standards will drop and we have to look for new standards again. This brings also those new algorithms are more complex. They require more memory access, more branches. So there is more opportunity for leakage of information. And when I mean leakage, I'm not speaking about the security, the mathematical security of the algorithm themselves, but more the within the implementation and those so-called side channel attack. Side channel attack will probably be able to find new ways to get access to the data from those systems, but also side channel attack can be boosted by quantum technologies. And for example, you could have enhanced machine learning models that are able to perform the same side channel attack, but requiring less interaction with the devices, but also using quantum sensing, for example, ultra precise time measurement in noisy environment, going through the shielding. So probably those side channel attack can be boosted with quantum technology. There is still one thing that will not change. Let's assume that we are in this future world and not that futuristic in a way because the EuroQCI system is already deployed and used in many environments. And so let's assume that we have a secure cryptography with a secure channel that no one can tamper with. I would say that from a theoretical perspective, we would be in an equivalent situation that we are today with end-to-end encryption. And so regarding investigation, we are already not able to tamper with those communication channels and get access to the data. This is obviously a real challenge, but the thing is that, and I will only speak about myself in this case, when I'm doing forensic investigation, I'm typically getting the device directly the device. So I'm on one of the ends of this channel. And whether this channel is used with quantum security or end-to-end encryption, for me, I'm in one of the end. And at some point, the user needs to access the data. So the data is readable in some point. And even if we have the best cryptography ever, it's going to be still the same users. And users will still not be capable of remembering their own keys. And so I believe that passwords will probably survive the quantum revolution. So then the next question is, can we do quantum password guessing? And my answer would be yes, let's go for quantum password guessing. Because what is password guessing? Password guessing is an unstructured search of a key space, which is matching a known target value, which is typically the hash that we can extract from the device. And this problem is exactly what Grover was looking for. And so the Grover algorithm is performing those search. The thing is that to be able to use Grover algorithm for password guessing, we would need first to have the hash function implemented as a quantum circuit so that then it can be evaluated on a quantum computer. And at the same time, also the key space, the password key space is not exactly like the key space of AES key. AES key is really homogeneous. You have to try potentially all the keys. But when we are speaking about passwords, again, the human will have this tendency to select password that they can remember. So they are kind of easy. And maybe if we are able to represent this key space in this quantum state, we would simplify our problem. I am very lucky to say that I'm closely following researchers that are working on these two cases. And one of them is working at the University of Sorbonne in France, and the other are working also at the GRC. And I'm closely following their research because this is very interesting in the term of quantum password guessing. I just want to underline here that the quantum won't break passwords. It will just make bad password hopefully fail faster. So this is an enabler. So what about Europol? What activity are we doing at Europol? Oxana mentioned the report we wrote 2 years ago, but we have also organized roundtable on the transition to post-quantum cryptography because it's quite important to start those no-regret moves of identifying the device that we are using, the cryptographic assets and cryptographic technology, so that we can better start also this transition. And for example, there has been also this report published by Europol in January 2026 about the migration activities in financial services, because this is quite a critical work also to be done. I'm also working currently on the quantum and cryptocurrency. What will be the impact of quantum technology on the cryptocurrency ecosystem? And last year, we have started a strategy group on quantum technology, which is a group of law enforcement. We are discussing about potential use case, starting working on them to deep dive in this to see what is science fiction and what is not, and also raising awareness and organizing training among us. To conclude my talk, I just want to remind that, of course, quantum technology will bring great opportunities, but it's also new challenges. So what we should do is probably to pilot use cases and dig a bit more into them, and also continue to do training and raising awareness. And I can only be thankful for the Quantum Flagship initiative to organize those training sessions. They are very interesting, and I'm learning a lot in those. And also something that is very important to finish my talk is that quantum doesn't just give power, it also gives responsibility. Quantum will not change what law enforcement is allowed to do. We still need to respect our role, and we cannot go beyond this. So that's really important. And we have to make sure also that any quantum decision are auditable and admissible in court. Like we cannot say that it is true because AI said so. We should never say we cannot. We will never say that it is true because quantum said so. So we have to use quantum to guide humans, not to replace them. And I will finish with my typical slide when I'm speaking about quantum, because brace yourself, quantum is coming. So thank you very much for your attention, and I'm looking forward for the question you may have at the end of this talk. I'm giving back now the floor to Oxana. Thank you very much.
Thank you very much, Iwen, for your presentation and for inspiring words at the end. They are very well received. And I see a lot of things also from the participants that are sending applause to the session. It's very nice, and I welcome participants to write questions and comments in the Q&A box, and we will address them to Iwen at the end of the presentations. Thank you, Iwen. And now I would like to invite to our stage our second speaker, Dr. Michal Krelina. And I'd like to introduce him as he's a consultant analyst and a researcher focused on the security and defense applications of quantum technology. Michal is a co-founder and chief technology officer at QDev, which is a quantum security company. And he is an associate senior researcher at CIPRI, Armament and Disarmament, where he's specializing in quantum technology as well. In addition, he's also a member of a strategic advisory board of the quantum technology at the European Commission. And his professional interests span mapping quantum technology military applications, exploring its role in future conflicts, developing quantum countermeasures, assessing quantum technology risks and threats, examining the convergence of quantum and classical cybersecurity, and studying the impact of quantum technology on international security and peace research. He has also provided consulting service for various organizations such as NATO SACT, NATO GAPCC, and EUSPRA, as well as various defense, law enforcement, and governmental agencies. And importantly, he held his PhD in experimental nuclear physics. So Michal was also involved recently in some project investigating with Interpol, investigating the impact of quantum sensing on the law enforcement. And this is what we invited Michal to talk about today. So welcome, Michal, and the stage is yours.
So, hello, good morning. Thank you, Oxana, for the nice introduction. So I was asked to speak about a little bit about quantum sensing and imaging in terms of law enforcement. As Oxana little said about me, I really specialize mostly on military application or used by intelligence. And what's important, what Iwen said, it's quite different because very often they don't have, let's say, strict boundaries like law enforcement. So that can be sometimes a bigger restriction, but also a kind of bigger transparency. So from this perspective, especially quantum sensing, which is kind of the third big pillar after quantum computing and quantum communication, and still, as in a military application, we have quite a good ideas how quantum technologies could be used. In case of law enforcement, it's still kind of exploratory. There are very interesting directions, but nothing like fully, let's say, I would say, tested in environment in the field, as is done in a military case. So quantum sensing, in principle, we just sense something. We can measure some physical variables like magnetic or electric field, gravity, gradient, pressure, temperature, acceleration, rotation, time, even pH. From this perspective, sensing is typical dual-use technology, and actually, from all those three pillars, is the closest to some commercial and real use. So why quantum? Why quantum sensors should be more interesting than the classical one? The reasons are more. In principle, they work better with the noise. They are more resilient to interference and different environmental factors. And in general, the rule is that it's more sensitive. But it doesn't mean that is the only advantage. The advantages can different form. It can be higher precision, better signal to noise ratio, or even miniaturization. Some sensors, let's say, can have a worse performance, but they can be amazingly small. So even that can be an advantage for very specific scenarios. So from this perspective, the definition of advantage, or if someone prefer to say quantum advantage, it's let's say more complex than in the case of quantum computing. Also, it's kind of a big zoo in quantum sensing. Like you have different type of qubits, how you can physically realize. The same for sensing. We have some fundamental principles that we can use for different type of sensing or quantum imaging. Each of them can sense different aspects and has own advantage, disadvantages. Something can be room temperature, something has to be cooled down, or even to cryogenic temperatures around absolute zero. So just for some basic mapping between what physically we can measure, like we can measure time, magnetic field, inertial forces, and for what it can be used, like synchronization, radio frequency systems, inertial navigation, or alternative augmented navigation, brain imaging, or some kind of chemical or biological detection. So let's start. The technology that is the most close to, or which is already commercially available, is quantum navigation. Today navigation is mostly based on satellite system, which is nice. It's super secure. It is super precise. However, only if it's available. So that means if we are at the wrong place, wrong time, you can experience spoofing, so some faking signal, or directly jamming, so no signal at all. Or if you are in some environment like underground or underwater, you don't have a satellite signal as well. So for that, you need some alternative navigation. And of course, we have some classical, and we have quantum, which at some sense are even better. So we have a quantum inertial navigation, which is just quantum version of classical inertial navigation. That means we can measure each acceleration, each rotation. So then we can build every movement and set by knowing initial point, we can know what's your new position. And quantum in this sense should be just more precise. Quite a new field is, for example, air magnetic anomalies or gravity aided navigation. What does it mean? So it means in advance, you create a big maps of magnetic anomalies or gravity maps. Then you perform local measurement, for example, by on your plane, ship, or even drone. And you compare local measurement with those gravity maps, and you can get your absolute position. And it's something that is already here. In case of quantum inertial navigation, it's being already tested in relevant environments, including planes and boats. Magnetic anomalies navigation is something commercially available. Actually, 2 days ago, Australian company Q Control, they introduced their commercial system that is based on magnetic navigation. But be careful, it's a very nice device that represent the real true modern directions in sensing in general, because it's not just let's say sensor of magnetic anomalies, but it's a more universal device that fuse multiple information. It can take information, for example, if you place in the plane, it can be fed by the speed of the plane, the altitude of the plane. If the plane has some alternative navigation like classical inertial navigation system, this device is able to fuse all information together. Behind is some kind of machine learning, and then at the end it will provide you very precisely your position, more precisely than if you would use just magnetic navigation alone. And this kind of fusing and hybridization of sensing is in general, I would say, modern trend. In case of gravity, this gravity measurement is still a little bit, I would say, bulky, because this magnetic detection is quite small. Gravity not so small, but it's already being tested in a relevant environment. From perspective of law enforcement, here the use is basically the same by law enforcement or criminals. It can be used, today jamming is the cheapest way of how to stop satellite navigation, and many systems are stopped by these countermeasures. So this is exactly one way how you want to be. It can be just fallback solution, but it will work in case you are in some environment when you experience such situation. Second use case I have here is precise timing. Precise timing is something that is very long time with us. Atomic clocks are on quite some time. These quantum technologies, in sense, compared to previous first quantum revolution, there we work mostly like with a statistical aspect of quantum behavior. But in current quantum technology, in the second quantum revolution, we rather work with the individual quanta. So if we go at the level of individual quanta, we can play with the energy level of individual uh, quantum system like electron, ion, atom. And at this level, we have some interesting application like atomic optical lattice clocks that are even more precise than atomic clock, and there is quite a very nice potential how we can make it much smaller. So then application this precise timing is application that is pretty invisible but pretty important. It is part of this satellite navigation because each satellite like GPS or Galileo, each of them on board has like 3 different atomic clocks, so they distribute this precise timing. Synchronization in telecommunication, power grids, and network sensing, seismic monitoring, all has to be uh, synchronized with let's say with high resolution or with very precisely. But also we can improve timestamp integrity, especially multiple sensing, surveillance, and you want to be precise, especially in let's say sensing some electric signals that are very short. And today again, we have already some commercial products. Of course, very big difference is if you place it in just some calm place or you place it in a plane where it's vibrating, moving, so on. So, but we are on a pretty good way. My favorite topic is quantum magnetometry. So that, as the title is saying, we measure some magnetic field, and for what we can use these quantum magnetometers, they can be very sensitive, and some of them has a very good nanoscale resolution. So the applications, I have my 3 favorite. First, in the US, they have a program where they use this quantum magnetometry as a microscope that they can scan, for example, your microchip, and they either can see if there is some manufacturing problem, like something is broken inside, not properly manufactured, or if there is something extra, some condensator extra that can later act as a backdoor, so we can catch this potential malicious aspects. On the other side, the same things but from different perspectives is a example from a German cyberagentur where they explore if quantum magnetometer could be used as a side channel for side channel attack. So what to imagine? For example, imagine you have dedicated cryptographic chip. You place this high resolution and high sensitive magnetometer that can sense each moving current in integrated circuits, and because it can read all with some help of AI, it can, for example, extract private key. Okay, that will be pretty big issue. So it's in interesting direction of research. Still, it's a research. It's nothing confirmed. Or there is a very nice example of a mech scanner. So it's a brain scanner which is non-invasive. It's pretty small and will be even smaller, and very often it's pretty good candidate for future human machine interface. So it in the future again uh, sensitive and high resolution sensing in combination with AI. It can read your minds, and with this you can, for example, directly control machines. So that's a pretty hot candidate for such interference. From perspective of quantum gravimetry, uh, typical applications are like we can find a new oil field, gold, or uranium. From perspective of law enforcement, what I met ideas like there are some in-field experiments where they already can show they can detect tunnels. So especially I saw some proposal that it could be used by U.S. border guards for detection smuggling tunnels, on the border between the US and Mexico, ideally from drones, because we can see quite good progress in miniaturization of quantum sensing, testing them, for example, in the drone environment. So different aspects you need are approaching together. Quantum chemical sensing is something that I would say is very low TRL, but potentially very interesting because it can be very sensitive to specific aspects of molecules or some specific aspect chemicals. And at the end, it could be used for environmental monitoring, security and forensics, like identification of explosive or drugs, for medical diagnostic or CBRN from it's more military, but can also be relevant for law enforcement. And here I have some examples, like there already were quantum sensors for detection of infamously famous SARS-CoV virus, but also there are already quantum chips that can detect drugs and so on. So it's pretty promising. Then separate aspect is it's using quantum imaging for even more precise um, spectroscopy. However, as I said, it's pretty low TRL and a lot of research has to be done, but those can be very interesting directions. Being in the field of quantum imaging, so in quantum imaging, we use some photons, light. What is already commercially available today is quantum LiDAR, and these can be different concepts. Quantum LiDAR usually refer that you send individual photons at entangled you keep one is sent to target, it reflected, and you can detect. You can have a you can use, for example, for autonomous cars, because modern and expensive car they use a classical lidar, but even those can be let's say jump each other if they hit. But with quantum, it's like a top end in the future. And there are commercial products like this lidar, quantum lidar gas detection that is tuned to detect the methane leakage. But in principle, you could tune for another type of molecule as well, and remotely detect it. So again, it's a very interesting technology. But in this case, it's a hybrid. As I mentioned at the beginning, very often it's hybridization where actually they use a classical weak laser, but on the receiver side they use a single photon detector. And actually there are many more use cases. For example, quantum RF sensing, which is very interesting because usually your antenna has the size corresponding to the wavelength you want to detect. This at quantum, they don't need calibrations, and they have many more advantages. So you could they are more sensitive, so you could use for some faster signal intelligence, some triangulation, more precise UAV detection of some weak signals, for example smuggled device in, for example, in prison, or very precise fingerprinting of unique RF signatures, because at the end each RF source transmitter is slightly different, but also it's a very good candidate for terahertz imaging. Terahertz imaging, it could be alternative for X-ray imaging, for example, at the airport. Another aspect is again from the field of quantum imaging, quantum ghost imaging, which could allow some better visibility in the worst conditions. Or there are very interesting experiments on beyond the corner vision. So imagine you send some laser, and it 3 times reflect, like from the wall, go behind the corner, then reflect from the target back to the wall, and from the wall to you. That seems crazy, especially at the level of individual photons. Like there are so many photons, how you can know that this is was 3 times reflected? But thanks to property called quantum entanglement, we really can do. And Chinese, for example, demonstrated such a beyond the corner vision for a distance of 1 kilometer. So it's something that really was experimentally demonstrated. It works. So in conclusion, quantum sensing is something that is already here. It's something that at some level has a very low TRL, and we exploring application but some are already commercially available. You almost can buy and mount in your drone, for example. There can be some I summarize for law enforcement. Today it can be for use for navigation and precise timing, and later especially chemical detections I see quite interesting uh, aspects or tunnels detections. But still, as I mentioned, and actually even said too, first these technologies will be primarily used by military and intelligence. Law enforcement probably will be there a bit later. But anyway, it's good time at least to stay informed and prepare. And still, it's nothing like, yes, we have quantum, we don't need all things. No, you always you will use all the tools, but this is new that can combine, and it can have some advantages. So very shortly, at QDev, as was mentioned, we are a security company. We build something we call threat and risk intelligence platform. We provide intelligence on security and military quantum technology for NATO, for the German Bundestag, or Dutch Ministry of Defense, and we also develop some quantum technology monitoring systems. And the last slide, because as was mentioned, I'm also affiliated with the CIPRI. So if you are more interested in the security from policy perspective, I invite you to read these two our reports. Thank you.
Thank you very much, Michal, for introducing us to so many use cases and such a close to reality and already in reality quantum sensors, and also giving some perspective on what will come in the near future, probably. And now we are all set to start the question and answer session. So welcome, Iwen, as well. And I will go directly to the question and answer box to read the questions. So first question I would like to bring is regarded to the difference between Eastern and Western country approach. So there is mentioned that Western countries generally favor post-quantum cryptography, while Eastern countries tend to support quantum key cryptography. And the question is whether you can explain the reason behind this and divergence in approaches.
I think it's quite complex to answer this question because I don't have exactly what the Eastern country or Western country have really in their mind. But I would probably underline that there have been some fear that most of the standards have been deployed by NIST, and some people are questioning the validity of those standards because NIST is an American organization. And even if personally I have no doubt, because NIST is making a world goal and they have been analyzed by world experts, and many solutions are coming from Europe. Maybe some of the Eastern countries have still some doubts that those standards are not controlled by some government view. It is rather easy for us to say it's not the case, but it is harder to convince. So that's probably would be my answer to this. But again, personal opinion and no conviction here.
Maybe I may add. I think it's a little bit of misunderstanding because you need to use PQC always and everywhere. Because imagine just your simple laptop. I have 5 emails, VPN, 20 open pages. Everything is using some encryptions, exchanging key with the different servers across the world. There is no way we will manage all this just purely with QKD. So PQC is just like has to be. QKD can be extra defense, and yes, there is a slightly difference, let's say, between how much is QKD prefer. I mean, to use because especially in the US, they think maybe QKD we don't need, and because there is in general lower trust in QKD. Whereas, for example, in China, they have quite advanced quantum networks. They have operational QKD networks. So for highly sensitive aspects, they use a QKD as additional layer of the defense. And the EU, we can expect something similar with EuroQCI because it will be very similar principle. So in the Europe, when this will be ready, and the EuroQCI is at least part of that is supposed to work at the level EU secret. So it will be dedicated like extra security layer for highly sensitive and classified information. So it's better framing like that.
Thank you very much, Michal and Ivan. And yeah, so I think that there is quite a complex multi-layer answer to that question. The another question from Sebastian Krug, and he is addressing it directly to Ivan. How and to what extent is the parallel progress in AI suited to increase the challenges?
I think I will reuse one of the last word of Michal in this case, that quantum in itself will not be a new technology, and we will not drop everything existing, the old technology. Quantum is more a booster or enabler of existing technology. That some of the things that were not possible today due to the limitation of the current models would be made feasible with quantum. And in what regards machine learning, for example, we can face some issue with very large size of data, or also very narrow points to go with. And that's where I think that the quantum will be a booster for machine learning. And so everything that is today possible with machine learning will probably become even faster or easier being used together with quantum. So that's why I think that the challenge we are facing today with machine learning and AI will not be, it's not going to be a revolution with quantum technology, but just faster and easier for them. So that's why I think it will increase the challenge.
Right. Thank you, Ivan, for this reply. And for Michal, so there was, sorry, pardon a moment. We are very full with questions. So I will go to this one. What is needed to mainstream quantum technology for security? And are we taking the necessary steps for speeding this up?
Okay, so that's a very general question. I mean, we already have quite a functional ecosystems. In sense, we have startups that are working, of course, mostly in quantum computing, communication, but we have quite some also in sensing. The difference is especially in the future market size, and there is a big support from governmental side, either in the at the EU level with the quantum flagship, different calls focus on quantum, but similar things we can see in other countries. A lot of countries they have already some kind of national quantum strategy that set like priorities, ideally, or they do everyone everything. That's not ideal. Some kind of education. Typically, very often part is some kind of funding scheme. So I would say for those who are interested, there is quite a lot of resources and even a lot of available free material. So if someone is interested, it's easily accessible. More difficult is like business aspect, especially for from perspective of startups, because imagine if you will be a quantum software startup, but quantum computers will be there like really useful like in 5 years, maybe more. So it's a little bit more difficult positioning from market and business perspective. So those are some specificum, but otherwise it's I would say available from my perspective.
Mm-hmm. Thank you, Michael. And to Ivan from Matilda Chenou, you briefly mentioned it, but could you develop on the side channel attack for classical or post-quantum devices? Would it be improved by quantum computers?
Okay, so regarding side channel attack, I think you can see this as a 2x2 matrix entry in the sense that you can think about classical side channel attack and quantum side channel attack and going against classical cryptography and post-quantum cryptography. So as we are developing new post-quantum cryptography, we should not forget that post-quantum cryptography is not quantum cryptography. It's in fact, it's classical cryptography. It's using still mathematical approaches, and they will be implemented in classical devices. And so as we are able to do today side channel attack on the current devices, we will probably be able also in the future to do this in the new devices that will implement post-quantum cryptography. So as this is going to be also more complex, there will be lots of possibilities to do these approaches on regular side channel attack. Can this be boosted by quantum approaches, quantum technologies? I'm quite convinced about it because first we will be able to use machine learning boosted by quantum, so that probably we will need to interact less. So what we call collect traces, interaction of the devices that we are measurement, the power consumption, the electromagnetic resonance. And this, after that, we have to learn about this, and we are using statistical approaches and machine learning to be able to detect what could be the key. And as AI can be boosted by quantum, these side channel approaches can also be boosted. And at the same time, as Michal already talked a lot about it during his presentation, there will be lots of refined quantum sensing. And so in side channel attack, it's very important to have very precise measurement. So with using quantum time measurements, we will be more precise, and so the attack can be even more precise, whether we are speaking about current cryptography or post-quantum cryptography. So the answer for me would be side channel can be used on both the current one and what will be quantum safe devices. And yes, it can be boosted by quantum technology.
Thank you very much, Iwen. Thank you very much for this detailed answer. And the next question would be regarding to your statement as well, that you mentioned that the first QC quantum computer will not be available to criminals. This was your personal opinion, and the question though turns it into the fact that, but it could still become accessible to the developed states or governments that do not always share the EU values and objectives. So in your view, which country or region is most likely to develop the first quantum computer? Is there exist a plan to develop a United Nations international or regional framework or standards that regulate its use or governance? What's your view on that? So it's interesting, the United Nations one. We have the European one, but whether we have the United Nations network of quantum computers.
Yeah, it starts to be a little bit more political discussion here, where I'm not as confident as when we speak about technological and technical questions. It is indeed a true hope for me that the first quantum computer will not be in the wrong hands. And by wrong hands, you can hear whatever you want. But it's at this stage, we are speaking about quantum computers prototyping, and I'm not sure that the companies that we knows and that are very famous regarding their publication and are mostly Americans, I'm not sure they will be giving access to criminal organization. I'm not saying that criminal organization will never get access to those devices, because I also believe that quantum computers will become more and more common and accessible with reduction of price, reduction of usage. Regarding the member states that are not sharing the same value than EU, yes, that is indeed a possibility. And we need to investigate into this and be prepared. That's the best, because it is quite for sure that this will happen. So the best thing we can do is to prepare ourselves and to understand how we can better prepare ourselves. Again, the transition is one of the best way to prepare for this advent. Regarding which country will be the first one to have a quantum computer, this is a little bit biased questions, because in a way the quantum computer already exists. It's just that they are not usable or today to break cryptography. But you can, if you join this quantum experience from, I think it's IBM, and there is also the Euro, sorry, I forgot the name, Euro HPC initiative that give you also access to some quantum simulators and quantum computers. So they are already available. It's just that today you can't make a massive usage of it. It's for research, it's for experimentation, which also answer, by the way, a question about training. So you can train yourself accessing those devices. So who will be the country that is the first one? I think the question should be then, who will be the first one to have a quantum computer that can break RSA? And again, here it's very speculative because you can see those using superconductors that are advancing quite well is number of qubit, but there is still this glass ceiling where regarding the error correction. So if tomorrow they are able to make a breakthrough in this error correction, they could be the first one. And so then I think US is more advanced in this. But then if you look at the other possibility to build quantum computer using ion trapped or lasers, lights, photon beams for quantum computer, I think then it would be more in Europe that we would be the first one to get access to this computer. So I'm not good enough regarding quantum computers to answer these questions, but I hope I've been able to bring some food for thought here.
Mm-hmm.
Maybe I can a little bit add from perspective of frameworks. For example, at the UN, there are departments like UNIDIR or UNICEF. They have some programs around quantum. But from perspective of security, a lot of basically most of countries that they already have some development of quantum computers. There is export control that limit. You can not export a quantum computer or its components without permission. So that's already a tool you can use today. And yeah, I agree that a quantum computer will not be immediately available to simple criminals. It's a good reason to expect that it will be firstly used by intelligence. And of course, then we can speculate what intelligence will try to break first, if some diplomatic messages, or they will try to break some information regarding some industrial secret, and then they put their own industry, or some break-in secrets they could, let's say, provide some state-sponsored actor who will act upon. But that is very, of course, speculative. But the expectation that the first quantum computers will go to intelligence organizations, since quantum building big, real useful quantum computer will be very expensive. Very often there will go money governmental, so you can expect they will want to have some use.
Thank you very much for reflecting on these highly speculative questions. And I'd like to go to a much more pragmatic one. What kind of materials, raw materials, are needed to develop and sustain quantum technologies? And where are the natural resources located? If you could reflect on that.
Okay. In general, quantum technology is not only sensing but computing and even communication. They also need some rare materials, and like in semiconductor chips, actually for many approaches you use the same manufacturing devices. So that's in principle the same issue of supply chain like you have for in other high tech industries. And there are already some nice mapping, for example, from Quantum Delta in Netherlands on this topic, and there are more and more publication. For example, UNIDIR is going to have one publication soon out. And one specific, for example, very common aspect for not all, but for many quantum technologies is that it has to be cryogenically cooled. So here we use helium-3, which is not, let's say, naturally available. Very often it's obtained as byproduct during the nuclear weapon manufacturing. So that's one quite scarce source. But otherwise, it's in principle the same supply chain issue like in other high-tech industry.
Okay, thank you very much, Michal. And we are coming to the closure of our session. And I would like to come to actually one of the first questions of the session, which is asking about possibilities for training, and particularly online training maybe, on these aspects of quantum encryption. So Iwen mentioned that there are some training opportunities that he's involved in, and maybe also Michal, could you maybe share with the participants what are the options to learn about these subjects, in addition to this training, of course?
Regarding training, so the one we are doing, for example, in the strategy group, this is more we are demanding and not offering. And
Okay.
so as a strategy group, we are gathering, and every meeting, we try to invite some experts to debunk and explore some more possibilities. And so, for example, last time we organized one of the presential meeting together with the University of Twente in Netherlands, where we could benefit from their expertise. So we are more demanding than offering. But I can refer to one training I did. So it's I don't think it's outdated, even if it's 4 or 5 years ago. That was offered by IBM directly, and so you could learn more about what it means to write quantum codes, and so using the libraries. And you can find many resources online to use Qiskit or QSharp, so that you can already start understanding what it means to develop algorithm for quantum computers. I think this is a good start because it helps you at the same time to understand quantum computers and quantum algorithmic.
Thank you very much.
From my perspective, if you Google, there are quite a lot of programs, some free, some paid. Even myself, I helped to create some of them. But if I should say which was the most influential to me, it's many years ago when I started with this field, the server edx.org. I did this program on quantum cryptography by Stephanie Werner and her colleague, and there was an advanced course. It's unfortunately it's not anymore active, but they have very details and dense resources part for free, like a whole textbook on really from mathematical perspective of the quantum cryptography. So that's my number one, I would say.
Thank you very much, Michal. And yeah, we have still a lot of questions, unfortunately, that we could not touch upon in this session. I thank very much the participants for being so active. And thanks a lot to Michal and Iwen for the presentations and for holding the questions and answer session. It was great to have you with us, and wish you all the best, and looking forward to see you in other occasions.
Thank you very much.
Thank you very much. Enjoy the rest of the day.